Well, anyway, thank you guys for coming, and thank you, Billy, for all the work you put into this, and Lake, all the work you guys put into this. We've been working on this kind of collectively, but really you've shouldered a lot of the load, and we appreciate that, making us look good.
Yes, we do.
So without too much delay, let's talk about how performance begins at the surface.
Well, I'll say this, it's kind of an anecdote. You could almost rephrase this. This is what I wish I knew 5 years ago. Because after working at Driven and Gibbs for almost 20 years, this is the single biggest variable that I did not know.
I feel like so many times what we're about to talk about is the real explanation for the age-old, like, I don't know what happened, it must just be bad parts, right? Or this racing engine failed, we don't really know why, so we just blame materials, or we blame, a bad batch. How many times have you heard that?
Right. Yeah.
So really, More Than Skin Deep is addressing those issues and how we can start looking at parts that we haven't looked at the same way.
Right, and things probably changed, loud, but okay. Things probably changed in the past 10 or 15 years. It used to be really hard to know what the material was that you're using. Today, you can take a slice of it, put it in a spectrometer, and it'll tell you your chemistry down, to a couple tenths of %. And what happened with that is there was reputation about bad steels coming in, there was different things coming in, bad heat treat. And so what you would get is somebody would take a piece and they'd cut it, and they'd have somebody section it, and they'd come up to Billy and go, hey, this went bad because it was 0.05 low in molybdenum. Now, you don't know how bad I wanted to just say bullshit. It's like, that what happens is if you go through your whole industry, over 90% of the failed parts are going to happen in the 10,000th of an inch between the surface and that first part of it. They all start near the surface. That's where the loads are the highest. That microscopic level, the applied loads were greater than the material strength of those 100 or so atoms around where that load was. And a tiny, tiny fracture starts in that area. Now it can propagate very quickly, and then you wind up with, it broke. So what happens is...
I always liked your analogy about potholes.
Yeah. No, I mean...
The pothole didn't begin as a pothole. It began as a small crack, typically subsurface, right? All you Michiganders already understand all this fact, right? What happens every winter? It gets cold. And that moisture in the ground, what does it do? It freezes. Well, what does water do when it freezes? It expands. So it breaks up your roads. So all the construction guys have jobs in the summer. But it's really almost the same thing, right?
Right, and you see it like if you drove up here and you went over a bridge and it was a concrete bridge, asphalt road, you'll see how as you come off that concrete onto that asphalt, they were perfectly level when they were done. But because this surface was harder and this surface was a little softer, it eventually started to put a little dent in here. Now as it went across there and hit that dent, then you created the high load. The material strength didn't change of that asphalt, but the load went up. Then you see a crack form near the surface, it goes down, then you have the spalling that comes up, it blows up. That's a macroscopic example of what's happening microscopically with your points, and that's what the presentation's about.
Yeah, so what we wanted to do with this presentation, somebody, it must be me, is squeaking, is talk about some of the technical aspects, but then also the practical aspects. So what can I do about it? So I know there's these issues and these problems, so what do I do about it at an engine builder level? So we're going to try and present it in that way so that by the time we're done, you got something useful out of this. So
okay, let's start with some slides.
Okay, here we go.
So we're going to call these, and Mark Malberg's in here right now, he's got to run, but I stole this from him. He talked about the two sisters of surface, and his two sisters were texture and contour. And what I did was, my mom was one of 3 girls, so I called the 3 sisters. So you have your surface texture, which surface texture describes your RA, your waviness, things like that about the finish. Like when you turn something on a lathe versus grinding it, there's a different texture on that very edge. So we're going to call this first part the texture, the second part the contour, and that'd be like crown on something, that'd be your big fillets, that's the geometry of it. And then the last but not least is the surface metallurgy. We do things like shot peen rods, shot peen springs, we nitride parts, but we can also damage parts. Rust is horrible. There's a lot of ways to do both.
Yeah, so we want to start with calibrating what we're talking about. What level of magnification, if you will, should we be talking about? So let's start there. So how big is a micron?
I love this because it's, when we talk about honing all the time, one of my first things I tell everybody is, hey, look at a trace of a cylinder. And look at the scale. Right? A typical Mid-Telio SJ210 scale is going to be probably plus minus 200 microinches. And I'm like, here, look at that wavy line, right? That's usually, most of that's around 100 microinches. 100 microinches is a tenth of a thousandth. So in a dial bore gauge, that's 2/10, a tenth per side, right? So when you start putting that in perspective, that human hair is, 4,000 microinches.
Yeah, that your red blood cell or a mold spore or silt in a river, is in the scale of what you're talking about, that 300 microinches plus or minus 150 microinches on one of these scales. Fine talcum powder, you're looking down to exhaust smoke area, not the fine particulate, not the diesel big stuff you see, but the little stuff that the CARB gets mad about is about 80 microinches. So you're talking about...
You can't see this with your eye.
So when you talk about, when people think like somebody picks up a valve spring and they leave their fingerprint out with the rust. Well, that rust has totally destroyed that piece. Now, you think I might say that to sell more springs. Dude, if you touch it and get rust on it, you're going to buy new springs. I'm telling you this to keep you going from Mala and have to buy a new set of pistons. Yeah.
So when we talk about the surface, and we talk about grinding versus turning a piece, and we're talking about this, this scale of microns, we're doing that so we understand, like, what part of it, when we talk about the surface, are we really talking about in this little tiny scale? So, what part of the surface is the surface, right?
Yeah, and so you look at this is plus 200 microinches, minus 250 microinches. Mm-hmm. And you can see this whole trace, this is what you would get with the skidless profilometer going across. With the diamond looking at the whole surface. You can see we have contour here, we have roughness, we have waviness. And so you break it up and you can look at it and we can look at what's the roughness, what's the waviness, and what's the form. Now, like if you had a skidless profilometer, there's a water ski up underneath the diamond, and so you don't see the form or the waviness, you just see the roughness. There's a lot of information there, but remember, it's only 1/3 of what we talk about when we're talking about surface texture.
And this is really big for decks. We're talking about gaskets and that kind of stuff. It's easy to use the skidded profilometer on a bore and get the information that you need. But when you're talking about waviness on a deck, right, it's going to be really hard to see that. And that waviness on the deck is what's going to cause the leaks.
Path,
Yeah, exactly.
So I kind of did this up so you could just kind of get an idea of the scales of the three things. So if you imagine that blue, dark, and light blue line, that's your surface of your part. And so you can see that the surface texture and everything is up there on that dark blue line. You can see that's broken up into the waviness and roughness. But then you've got the compressive stresses you might have left over from nitriding or shot peening, and those could go up to about 10 thousandths deep. But really most of it's in the first 5 thousandths. Now what's amazing is when you look at HRC diamond indention, that when something's about 62 Rockwell, that only goes 3 thousandths deep after it preloads, so it's probably about 4 thousandths total. So you look at this as a 60 Rockwell, when you hit it, you've gone through almost all of your surface. It's kind of like trying to learn about the surface with the HRC gauge. Is like duck hunting with the 155 millimeter howitzer. You might have killed the duck, but you'll never know.
All we know is it's not there anymore.
Right, it's just not there anymore. The feathers are gone. It's like, yeah.
So the biggest thing when you're talking about texture, and I know Mark hates it when I say this, there's way more to this than RA, right? RA can easily lie to you. And in my world of piston rings and cylinder sealing, that's the biggest issue, is that you can have very different surfaces with RA, same RA, very different surfaces. So that's why we talk about things like RVK, which for me, you guys know me, I love oil. It's my best friend. It's your piston ring's best friend. You got to give it a place to be, right? And we're going to talk about that a little bit more as we go on. But you got to have a place for the oil to be. Your RK that's where the rubber meets the road. While that RVK is that valley, it's the reservoir, but that's not where the surfaces are interacting. What's that load-bearing area? So that's where the RK becomes really important. And then you got things like RPK, that's the peak heights, that's the stuff that's going to probably turn into debris more times than not. So you got to be careful on that, because if you are generating a lot of debris, if you're trying to hone the engine while it's running, it can be pretty bad.
And you might need a RPK for certain gaskets, like some of these tri-layer, 5-layer, 10-layer gaskets.
Yeah.
Like to have something to bite it, so that RPK that's horrible on rings could be good on gaskets, and that's something weird to learn.
Comes back to application, right?
Yeah.
And one, you're trying to knock that peak off, and the other one,
one
you're
of them
trying
may
to
not be bad. One of them may, something's got to have teeth and something doesn't.
Right, exactly.
So to your point of RA can fool us, right? So here we go. This is the slide we talk a lot about in our honing classes and stuff, right? So, you get the same RA.
Yeah, they're roughly the same RA, from a 2.4 to a 2.5, but your eyes will tell you, well, those aren't anywhere near the same.
No.
And the load-bearing area will not be anywhere near the same. And so it's really, really important to make sure that we have a better way of defining that and understanding it. And that's really where we come back to, I said, the RPK, RK, RVK. When we use that, now we can begin to really quantify what we're doing and visualize it. And we talk a lot about the numbers, especially when it comes to honing, right? What kind of RK do I want? What kind of RVK do I want? And those are good, but those are for sanity checks. You want to look at that trace, because that's the thing that's real. When that profilometer drags across that surface and is creating that picture, the picture is the real thing.
Well, we say a picture is worth 1,000 words, right? And I think the first time when we were honing and we started looking at this picture instead of 3 numbers that were just randomly chosen, right? So like before, when you would hone a block, you could test your profilometer in 5 different places and get 5 different readings, right? Because all you had was these 3 points in space that you were looking at, and then suddenly we got this image that the picture tells the story.
Yeah, and I'm not trying to sell anything in the world, but like my friend Mark, digital metrology, they have that TraceBall software. And what it does is it starts making you look at the pictures. And what's weird is you'll find out if you spend about 2 or 3 years looking at the pictures, then all of a sudden it recalibrates your mind so that the numbers make sense in a way that they never made sense before.
Yeah,
Yep.
It's huge. So this is my favorite slide, by the way, right? The oil nerd in me can't help on this, right? You guys who were here last year, you probably heard me talk about it. We're going to talk about it again. So this is a 3D profilometer trace of a section of a used cylinder. So if you take a full cylinder, now imagine taking that cylinder and actually cutting it into a small little coupon. Let's take that coupon, let's set it on a device. Take a section of a piston ring, and we can put that piston ring on that cylinder, and we can rub it back and forth, just like it does in the engine. And we can change the heat of the oil, we can change the load, we can change the speed, so we can basically run it like it runs in the engine. Run it back and forth for a while. What you're looking at is at the very end of that trace. So that far left-hand side of the slide is the unrun part of this one little section of that cylinder, where we've taken the 3D profilometer trace, unrun, and then the run section.
So basically the red is where the ring stopped.
Yeah, basically that little green valley, you see that at the very end? That's where the ring stopped. Do you notice that it's kind of shallow like this? You know what your ring face looks like? It's a barrel, just like that. Who's ever been water skiing? Everybody understand the concept of water skiing? When the boat is not moving, where's the water skier? In the water. As the boat begins to move, what happens to the skier? They begin to come up, right? Once the boat's at speed, where's the skier? See, y'all are all lubrication specialists now. You've passed the test. What you see here is that what happens twice each stroke to the piston ring. It comes to a complete stop. You guys are great. I love y'all.
So it's transitioning right there between the boundary layer, the mix layer, and the hydrodynamic.
Exactly.
And what's the cool thing is if you've ever water skied, when you're behind the boat, it feels fairly smooth, and you get out to the edges, it gets rough. That red is the waves that the boat hasn't knocked down.
Yeah, exactly, yes.
And then what the crazy thing is to get back and step and thinking like, you look at this surface and it's shiny and it looks beautiful and everything. You run your fingernail on it, looks pretty good, doesn't make the hair stand on the back of your neck. But that's what a surface really looks like.
Yes.
That's a real surface there. So when you think about surfaces, they're not this beautiful homogeneous thing. They're a bunch of atoms that have been processed and machined, and they're making a contour like this, and your parts are rubbing on that.
Right, so everything in red is what you would call RPK. Everything in green is pretty much most of your RK. And then everything in blue is pretty much your RVK. Isn't that cool? Isn't it easy to see? It's like, oh, I get this now. Makes total sense. One neat little thing, back to our water skier. You notice on the right-hand side of the slide it's getting a little more red? That's because that oil film is getting thicker. As our speed's increasing, what's happened to our water skier? It's coming up out of the water. Right? So you can see all of these different things kind of functioning in practice. Now,
So this time last year, if you know Lake, he was totally geeked out about this slide,
Yes.
right? So we've had a whole year to now think about it and work on it and go, this is what we talk about when you say, well, we hone our block and then we use our profilometer, but then we run the engine
Yes.
and we take it apart and we use the profilometer again. It's like, hey, it's trying to talk to us over here and tell us what it's doing. And it's so funny how last year this was like, you got to check out this slide. This year it's
Right,
like,
yeah.
let me show you what this slide means.
yeah, well, the cool thing is, okay, now what actually happens, right? So, of course, you guys know me and my buddies out at Shavers, we're always messing with stuff. So that upper right-hand corner, that is a traditional 280 grit, conventional stone finish, been used in sprint car engines for years. I mean, if you want to go out, lots of races, lots of championships won using that finish. On the bottom, that is a true plateau finish. That top one is a single grit finish. The bottom one is a true plateau finish done by Brad Lagman, who's a good buddy of ours. And we said, hey, we think that with a methanol-injected engine, the amount of fuel going in, especially mechanical injection, we want more valley. Because we know pretty much on that top one, that ring is going to come by, and just like that previous slide, what's it going to do? It's going to knock all that stuff off. And there will be some valley left. Man, but it probably isn't enough valley. So what we want to do is we want to create a ton more valley to begin with. So you go in with about a 140 grit diamond, and we make these really big, deep valleys. And then we come across the top of it, and we begin to knock it down. So now we're able to create a much smoother running surface while we still have tons more valley to hold the oil, to lubricate, and to seal. So what's neat is when you take these kind of finishes, and then we put them back in our little test device, and we look at, well, how does it hold up over time? Well, that single grit finish on top, can you see much crosshatch left on that top one? Nope, because it doesn't last. 2 reasons it doesn't last. If I don't have enough valley to begin with, you can't add it later. The other thing is, what happens to all those peaks? Where do they go? We wish they would just go straight to the oil filter and not pass go, not collect $200. But the reality is they don't. So think about your conventional honing abrasives. Why do you have to change them so often? Because they wear out, right? Well, that silicon carbide or silicon oxide that's in there, what's it doing? It's coming off. It's breaking down and is acting as a third body abrasive. Those peaks are third body abrasives being held by your oil, and you are basically polishing your cylinder. That's what's happening right there. Now look at the plateau finish. Now, nowhere near as many peaks, run it for the same amount of time, and you can still see the crosshatch. You gave it the valley. It doesn't have to do as much work because now we have a closer to running surface to begin with, which is huge. And again, this is just cylinder stuff, but don't think for a second that all of this is about honing. It's not. There's so much more to this, right?
But no, from a practical standpoint, I want to make sure that we don't miss the point that you made there, that if you are honing a block, though, if you start with your grit, too fine, and that first cut doesn't get valley, you don't magically get more valley later by going to a 600 grit or a 1,000 grit. That valley is just not there. So you have to start out with it and then get your plateau later. There's no getting back to that valley if you didn't put it there in the first place.
No, one of the things I've shown this presentation from the honing class several times in the last 2 days, that if you have a factory block in your shop, you have a factory block with Darton sleeves in it, and you have something, maybe something else that's different, harder, higher nickel block, and you have the same abrasives, and you use the same honing processes, and all 3 blocks, you end up with 3 different finishes. And we can sit there and show you that, right? If you want to come by the booth later, I'll show you the traces, right? In our honing class block, we actually have, it's a factory LS block. So one side is factory material.
Yep.
The other side has 2 melling sleeves and 2 Darton sleeves. And we will hone all 8 holes with the same abrasives, and you get 6 different finishes.
Same load, same speed and feed, right? But you end up with the differential between the hardness of materials, you get a different finish.
Yep.
And it's amazing that a lot of the characteristics when it comes to honing, haven't changed what the engine really wants. So if you had an old school deal and you can measure it and see what, you had a block, man, this thing was great. Well, measure it, learn about what it wants. The difference between now and then is, it used to be like in pro stock when Steve Schmidt was doing these things, if you ran it the first couple of pulls and it wasn't doing right, you just kept running it, and it got better and better and better. And now in a modern pro stock motor, if it's not good by the second or third pull, it's never getting better. Yeah. So you've got to, now instead of trying to put a surface and let it work into something good, with the modern rings and some of the modern bores, you have to go ahead and start with what you want. And to start with what you want, you have to really look at these graphs. That's where some of the software really pays off, is it shows you what is a good surface really like, and then you can work backwards and go, how do I make that surface?
So what you started out with was, gosh, I wish I would have known all this stuff 5 years ago. And so if you think about what's really changed in the last 5 years is, Billy, you said it perfectly, like realistically in terms of honing, it used to be all about the honing process. Now it's about the honing product. We're trying to get to a finished spot at the end instead of, well, we always do it this way, this stone, this many strokes, this much. That doesn't matter. What matters is the end product, but we only got there by understanding what the surface needed to look like.
Yeah.
Right? So we don't care as much about your process as we do the product.
Yes.
Right. And now this is going to sound like a complete infomercial, so just know that right now. It is not. It is not. Where we were 5-6 years ago when we were doing oil development and we were trying to figure out how to make oils better. Well, most of our engines, where's the weak spot? Most of where? Valve train. So we got to focus on the valve train. So me and Billy, oh my God, I don't know how many countless camshafts.
It was hundreds.
Yes. And that little small block.
Because we were doing 12 at a time, and we did them like once a month, and they all had to be identical. Every low bone was identical. No parkerization, because that would change things.
Right.
Small base circle, hard, really small tip, lots of load.
That's one of them on the picture, by the way. So that's a flat tappet. And so we had these flat tappets, like I said, small base circle, real small nose radius, a whole ton of valve spring pressure, no parkerizing, and poor Chris Potter and these guys. Every one of those got add cold, all 16 lobes, profilometered, all 16 lobes, and we would go put them in an engine and run them for 30 minutes and then pull them out and then fly them back to Memphis from California, 4 at a time. We'd do 4 cams in one day. Fly them back to Memphis. Already have some other ones already been broken in, ready to go. They'd fly them back by Wednesday and put them in the engine and run race simulations on the dyno to measure cam lobe wear. So we were doing that over and over and over again. And when we were doing that, we were actually using Mark software. And one of the cool things, I remember we did this, right? Yeah. We took that skidless profilometer, because again, it can look at the shape, not just the roughness. And you can see that radius. Like if you took that flat tappet lifter and you actually measured it, you could see that, was that 36 inches or whatever it is?
It's 50, it's like 56 inches. Mm-hmm. Now what's cool is when you look at where I circled over there, the radius that wound up in the front of the camshaft, the top right is before it was run. and the bottom left, same lobe after it was run. And what the cool is, like you can see on the very bottom, on the very far left where it wasn't run, you can see where the lifter never touched. But through the middle, when they talked about flat tappet break-in, you have to understand, I said break-in probably a million times, but I thought it was a myth. You know, like, there's, whatever, it's a wives' tale. But then you pull this out, and, Lake, what? You're not going to believe this. What? I seen this thing, 68 inches. It matched the freaking lifter. And it was like that lifter was about 60 inches. The cam became 68 because it's averaging some of the outside the middle. But that cam, you could take that lifter plot and turn it over and it would just fit right in there like a glove. That the lifter and the cam lobe really did break in and match one another.
Right. And that's when it went good. When it went bad, it didn't look that way.
Yeah.
We have a whole nother hour conversation we could have about that, but we won't. But the thing was, back then, we were using, that was called Profile Master, right? Uh-huh. But that didn't exist for the SJ210 to be able to put it in the home. The thing that's changed that we didn't have 5 years ago that we have now is we have the TraceBall software, so you can have this same level of visualization for your home. That's the greatest thing that's happened. So now you can really, with this kind of software and these tools, you can see all of your surfaces in your engine, and now when you can see it, you can really understand it better.
Well, it's like we always talk about, until we could measure it, we couldn't manage it, right? And so nowadays, we change the way we do the process so that we get the product. But before, we never knew about the product. It was always this religious adherence to process, and that's why some engines would take 3 pulls and some engines take 10 pulls, and it just wasn't the same.
And you have to understand every application is different. Like, if you look at the gray lines in there, that's our target crown for a roller camshaft. But we knew that, hey, crown's great on rollers. Let's put crown on flat tappets. Well, you can see that a flat tappet really goes the opposite way. It becomes concave. And once you start understanding the geometry and everything, you understand why. And it's like, sometimes if you grind a camshaft, you see it's got crown, it's a flat tappet. It's like, okay, you got to throw that away or start over because, it's got to be flat.
It will be really, really bad if you have crown on a flat tappet. Ask me how I know.
Yeah. So this is kind of, when we talk about geometry, it kind of would flow right into this. People talk about a cam and a lifter wheel, and this is for a roller, and you imagine, okay, it's a flat wheel and a flat cam lobe, and don't be embarrassed. You want to sit there out in the audience and kind of put your finger out here like this and go, okay, if I push in like this, it hurts the knuckle, but if I crown that out like a Roman road or one of the aqueducts, it seems to work better. But that's not the way to do it. You should do flat and flat. Then you go roughness, so it looks like this. But if you start thinking about it more, when I started work, we'd mic the sides of the lobes, and on roller cams, we'd look for taper, or you'd look for flatness where the dress was over there. And you could just catch that, just run it over with a micrometer. And you go, okay, well, that's bad, and you understand why it's bad. On both these applications, remember, what's a failure? When the microscopic loads are greater than the microscopic material strength at that location. What happens when you do that? Well, it puts high load on the left-hand side and it fails there. Duh, it goes boom. But it can be really weird stuff too that's hard to see with the mic. If you go left to right and you mic the side of the camshaft and it has all that waviness in there, it's still going to hit those high spots. That concave camshaft, remember concave so good on a flat tappet? On a roller, it's a guaranteed snake bite. That's why they GM puts crown in there. So you started to deal with a lot about surface contour, and this is our second sister. Only the loaded geometry matters. It doesn't matter what the geometry is with no load. It matters what the geometry is and loaded. And you see this so much with crankshafts. You guys see some of the stuff that, with the more counterweights in there, more overlap, trying to get cranks. Because what happens is you'll bite the edge of a rod because the crank bends or something like that. So it's not and pin bores are amazing. Like the piston guys, they won't tell you all the secrets they do to get that pin bore right, so under combustion pressure that it spreads out those loads. But it's super important. So you can see what happened on the lifter side, on the cam side, is this wasn't something that Comp came up with. I mean, Cummins was doing this for 20 plus years. GM started doing it in the 90s. They did and put crown on the camshaft. But it's not just camshafts where it matters. You know, spreading out that load matters on everything. Look at these 2 lifter wheels. That's for the exact same application. Which one of it, when it's loaded, is going to edge load? And you can imagine what you're doing. Think about this. This is a lattice. This is a bunch of iron atoms hooked up to one another. When you go through that lattice with a razor blade like that lifter wheel on the right, it just puts a razor blade scribe in it. And that razor blade scribe creates a crack. That crack propagates and it blows out. That one on the left will actually run on the same exact camshaft. If you put half of these and half of those, the lobes on the left will last 10 times as long as the ones on the right. There's nothing that's changed about the metal of the camshaft. There's nothing changed about the heat treat of the camshaft. There's nothing changed about the material of the lifter, and there's nothing changed about the heat treat of the lifter. This isn't a materials issue. This is an applied load issue.
You don't care how much material strength you have, it's going to fail.
Right. I mean, the thing is that, you know, one of our good friends that worked at Cummins, we were sitting here talking to him, and, you know, I was trying to figure out what material he ran. And he's like, you know, because we'd done some cool tool steel stuff, worked with carpenter steel, and it was awesome. And I was as proud as a peacock. I was probably in my mid-30s, and, man, I was strutting. And I came up to him and goes, okay, what's your UTS, how many KSI UTS do you have? And he told me, and I was like disappointed. Well, what material is it? And he told me, and I'm like, well, I've got something that's like 20% better, you know, UTS. And he looks at me and goes, well, I've increased mine by a factor of 10. I'm like, you can't increase, all steels are somewhere between 100 KSI and maybe 350 KSI. You know, most of them are between 150 and 350. You can't make it 10 times as high. He goes, yeah, but I spread out my load over 10 times as much area. And I was like, son of a, yeah.
Got him.
Yeah, it just totally busted me. But I learned a lot that day. Usually when you're embarrassed, you've got a really good opportunity to learn. That LS rocker arm right there, if y'all flip over a factory rocker arm, notice you'll see a little imprint on the back side of it. That's because they're coining it. What they're doing coining it, we'll talk about later, is compressive stresses, but they're also creating that geometry. If you look at that roller lifter on an LS3, LS7, or even an LS1, it is not flat across it. There is a sophisticated geometry, and they work their rear off on that. So what you do is, I think the thing is that, guys, pay attention to failures. They're telling you so much. Like this camshaft failure, you know, what we talked about is measuring things before they're run and measuring things after they're run. Mm-hmm. Sometimes you won't have the opportunity to see it before it's run, but when it's run, measure it. The more you can measure, making data-driven decisions is kind of like the key to being a professional.
Yes.
You know, amateurs guess, professionals measure. You know, you get in here and you start taking this profilometer and you measure the camshaft that failed, and all of a sudden you see something like this. And you start looking under a microscope and you can see where the edges of this lifter, this thing had a flat dress on it, there's no crown, it had some taper in it, and you can see the side that had the taper high. Remember, we're talking about things that, I mean, a human hair is bigger than the room right now, okay? Y'all got that, right? Your hair, I mean, I don't have many, but, you know, if I had them, they'd be bigger than the room. Yeah. You can see the dress in here. You can see everything about what was going on. You can see some oxidation in there. But you can see how that edge of the lifter did exactly what I said at the top of the screen. It put a razor blade in there. It put a scrack in there. And that is what caused all of the issues. And you can see exactly what's going on. You know, people go, okay, well, I'm just going to polish the camshaft. Okay, great. Well, this camshaft is absolutely shiny. But the problem with doing polishing is it's really easy to put more pressure in the center than on the edges. It's hard to, and so what you wind up with is this bathtub deal. Now this thing was shiny as it could be. It was about a 14RA, so not great finish, but it was you know, the waviness on it is 127 microinches. So top to bottom, you're talking about, you look at on this graph, some of these, that's the average wave. You can see from peak to peak, it's going down almost 0.3 of a thousandths smaller in the middle than the outside. Now it's hell to measure that with a micrometer, but it's really easy to do it on a profilometer. So stuff like that, just because you polish something, you might not doing it right. You can see that this is a GM stuff. This is a first generation LS1 on the very left, and then it's a modern LT on the right. And you can see that GM has gone in there and put significant crown in it. Now, part of the reason they run crown in there is if you ever take out a used, if you take an old 300,000 mile Chevy apart and put it crown, you look on the base circle and you'll see that the wear pattern's really narrow, and then it gets wide in the flank, and then it gets narrow, and then it gets a little wider on the nose. Well, that's because they put a ton of crown in it. What they're putting in the crown is they're making sure if they have some taper in that lifter or taper in that lobe, that they're not going to bite that edge, because they know if they bite that edge, I'm dead. So, and you can notice if you look at the geometry, it's not a pure crown. It's actually got a little parabolic. It goes out more on the edges than it does. So they were super sophisticated in this. But if you look from the 90s to today, what was kind of cool, I can walk over here.
You can.
Is if you look at this little number over here, this RMR,
yes,
that's the material ratio. And you can see that if you look at this camshaft they did in the 90s, at 10 microinches, it only had about 9% surface area. So if you imagine the snowshoes and over here, only about 9% of the area of the shoe was actually touching the camshaft at 10 microinches. And it was only, when you go down to 20 microinches, it was only about 18%. But you look at the camshaft that they made, 10 years later, 10, 12 years later, and they've gone from 9% to 45%, and from 17% to 85%. This is what my friend at Cummins was saying when he said, I've made mine a factor of 10 better. From 20, that's getting in there. That's getting toward the, 5, 6 times better, performance there.
Well, it's like, how many push-ups can you do on your fingertips versus your palms?
Especially
really,
from
that whole cam, it's like doing fingertips on like my thumb and my pinky. You're barely doing any, right? That residual, it's pretty cool. That's just.
So one of the coolest things I was involved in with comp is we started before, the first thing we did is, like, I wanted to polish, and Scooter was, he's always Scooter, and he's like, if you can't grind a camshaft right, we're not going to try to make it right with polishing. And he was absolutely right about it. It's like, how good can you grind it? So we started putting a little crown in it. Because our loads are higher, we can't run GM crowns. If we run the super high crowns GM, we'll flake out in the middle of that track on the nose. So we have to spread it out and use more of the lifter. And then we have to hold our taper tighter and make our lifters better and things like that. But what we find is, like, when we ground the first cam, we get this guy on the left, and you can see that it's, running about 50, about 6 RA, about 50% RMR at 10. But by the time you ground 40 camshafts between a dress, that wheel had broken down, and you're getting back from 50% toward 20%. And I'm showing Scooter this, I'm like, we can get a good dress, but it's hard to hold a good dress. Now, we still got excellent contour. We just don't have quite as good of RMR. Now, you have to understand, we were, right there, that's 45%. We were like 15%, if you went back 15 years. So it's excellent, but it's not. When you've seen 80%, it's really hard to go back to 40%. You know what I mean? It's like the guy goes out and, runs 12s. It's really hard to go back and run 16s. So what we did is we did exactly this. We took that deal and found a way that we could grind the profile the way we wanted, and then after it was ground, go through and polish the peaks off. Now, the process that we go through here is kind of like mowing the grass. You can't go in there. If you're going to build a Major League Baseball park, you can't go in there as a finishing mower. You start with a bulldozer, and then you get a grader, and you do everything. You lay down some dirt, you pack it down, and then you go with the finishing mower after you got the grass growing. And it can look awesome, I guess. You can see that this finish was very much like that last finish, except now it's 55% at 10 microinches, and we're up to 95% at 20 microinches. So at 20 millionths of an inch down, you've got 90% of the surface area there to hold it. So compared to a camshaft of old that was 14%, and the wear resistance on stuff like this is just amazing.
Don't turn it over yet.
Okay.
Does anyone notice how similar that bottom graph looks to a honed plateau cylinder? Who wants to guess which came first, this or what we're doing with honing right now? This is where it came from, right? Because we were doing all this together.
Yeah, there was ideas that if we made a roller cam too smooth, it wouldn't hold oil and it wouldn't do this and it would skid and all kinds of things. And it was going to do bad. And, you know, I mean, trust me, I went from NASCAR, we did 60 millimeter journals and people thought the needle bearings were going to spin so high that it ignited the oil and blew the car up. It didn't.
No. That is a beautifully plateaued finish down there at the very bottom.
Right. If you do it right, it's not going to.
No. And that's
you
the
can't
RA
make a surface too. You know, if you know what you're doing and you're aiming at the right stuff, you're not going to make a surface too good.
No, that's phenomenal. And the difference is, like, you can go too far, right? Was part of this process. If you guys have heard me talk before, you may have heard about my Gibbs story where we got the RA on cam lobes like this below 2. Mm-hmm. And basically it's just flat line. And we promptly blew them all up in practice because now there wasn't enough valley to hold any oil. And now we have no lubrication at that contact. And that's why I'm saying this is beautiful because you've got all that load bearing area, but you still have those valleys to hold the oil. And that makes all the difference in the world. We do this thing called the Engine Performance Expo every January. We're coming back January 11th and 12th, by the way. And a year or so ago, when we were working on that, we visited a manufacturer and we were going through some of their things for the expo. And they happened to mention that, hey, you know, you're an oil guy and surface finish guy. We have this wrist pin problem we're having, right? And they said, on paper, this wrist pin is the best wrist pin we've ever designed. And it needs to pass a 100-hour durability test for our OEM customer. And we put it in the engine, and it lasts maybe an hour. And it's galling the pin bores. And they can't figure it out. And I'm like, well, put DLC on it. It's the greatest thing ever, right? Right? And he's like, well, that's the problem. It costs a lot of money, and blah, blah, blah. And I'm like, well, okay, well, they had given us a tour through the factory before we had this little conversation, just literally in the hallway, right? This was kind of just off-the-cuff conversation.
I'm going to put the pin bore up while you're talking about it. Go ahead.
Yeah. So I said, hey, I noticed you had 4 centerless grinders in a row. I said, what's your finishing process, on this wrist pin? Chest pumps up a little bit, and he's like, we run 800 grit here, then we run 1,200 grit here, then 60 minutes, all these 4 minutes, every one, that goes across all 4 of them. I said, is the cycle time, stock removal, is it all the same? Yes. I said, I know your problem. He's like, what? I said, it's too smooth, right? And I reiterated the Gibbs conversation to him and said what we had, and he's like, really? I'm like, yeah, you made it too smooth, right? If you want to run it across, do 4 operations, that's fine, but do like 3 of them on the roughing machine and the last one on the smooth one and create some plateau. And they had skidless profilometers and everything, and I was like, you need to create a plateau. And came back about 4 months later, I got a package in the mail, a little gift box from them. And they said, all we did was follow your advice. We put it in, and it instantly passed the test and went over 200 hours with no change. Mm-hmm. They didn't change the material strength. They didn't change the geometry. They changed no heat treat. All they changed was surface finish, and it made that much of a difference.
It goes right back to the focusing on the product rather than the process.
Yes.
So they were so proud of this process. We do exactly the same every time. This wasn't producing the result that was desirable.
Can I borrow that line?
You can have it.
Okay. You're going to hear that again.
So, okay.
Yeah, and now talking about just about the contour, like on the pin bore, just like he's talking about on surface finish, you need contour too for the piston. Because once that combustion, that spark plug goes and it puts all that pressure there, it's not what it is when you're holding in your hand. That piston pin bore, and there's guys that will shoot you for showing this slide probably in this downstairs, so I hope they don't see it. But that pin bore isn't a straight, perfect hole. A lot of them are designed with a shape to them, and they're designed with a shape to them so when they're loaded that it spreads out over that bore so you're not biting the edges of the pin. And you've probably seen that on some really good pistons versus some mediocre pistons. Like you see that one of them's biting the pin at the edges and the other one looks like it's got really good wear, especially if you see it, you see why does this one look like this and this one look like that? Well, somebody figured out how to spread those loads out.
Like the crown on the cam lobes.
Exactly. It's
Yeah.
it's about trying to spread the load out. Sorry about that. Go ahead.
It's all good.
And the same thing applies back to the cylinders, right? We talk about cylinder finish, right? You're trying to create that shape. Well, the problem is you can't measure that that roundness with a dial bore gauge or anything that's only 2 points of contact. You know, if we had a bunch of poker chips right here, you could get a mic out and we could measure them and they might be all real close together. Mm-hmm. But you stack them up and offset them, they'll all measure the same, but they're not straight. Mm-hmm. You know, so that's where you have to have an incometer to be able to do it. And you can see, you know, the cylinder bore, that it's round, but it's not always straight, and it's not always the same roundness. You know, so it's really about having that geometry right, no different than the pin bore or the cam lobe or anything else. For the cylinders, you want to have it as round and as straight as possible, and the only way to really do that is to have, you know, an incometer to do it. Unfortunately, I guess they stopped making them now, and they're really kind of expensive anyway.
But being able to, you know, you do everything you can to try to figure out what's going on, you know, stuff like an abradable coating, things like, you know, with those guys a couple of days ago,
Yep.
You can see what's going on, read your parts, try to look at that inspection side that I started with. That's important with this because you can see that there are things where it's loaded, where it's telling you things that, and you remember the guys that do the different strokes at the bottom and do the manual stuff with this. Now it's all CNC, but, you know, there was a lot of stuff going on there.
And that makes a big difference, right, is that without having an incometer, the advantage we can do is say, okay, the modern hones, be it a Sun or a Rottler, right, the vertical CNC hones, when you put more abrasives in the hone head, you get a straighter, rounder cylinder. And fortunately, they've paid all the money to go to Pat and have things tested they can see, all right? You know, that when you go from 2 to 6, you can see how much it changes in terms of how much rounder and how much straighter it is.
And no dial bore gauge will show that.
Never, not just the number of stones, but also the vertical portion of not falling through that arc on the older style. But that combination has given us much better geometry. Right?
Absolutely. And the machines are smart too, right? It's sensing as it's honing.
Yeah, because they used to look at the little current gauge, right? And they go, okay, it's pulling more current. That means I'm taking more material off. So if you watch Kazi, you know, bore a cylinder, you know, do the hone job on a cylinder, he was watching that current like a hawk when he was doing it. Well, these machines can do that. You know, it's funny. It's not like there's a new technique. There's just new tools.
Yeah. Right. And they're not, I mean, the guys who are experienced have been doing it for a long time. They can
hear it.
Exactly. They can hear it and feel it, right? They can, all the senses are factoring in. Well, the CNC is doing it through the sensors in there. It's feeling it and hearing it and seeing it too.
Yep. And the other thing that CNC has changed, though, is the ability for somebody that didn't have that 35 or 40 years of experience to be able to produce results.
You don't need to be 65 years old to do a good home job.
Right. Yeah. So, all right. Well, I really like this slide.
This is one of my favorite ones.
Yeah. So all the geometry matters. You start, and I'll fill in the comments.
Yeah. I mean, well, the whole thing is you're like, okay, well, geometry matters on the piston. Well, geometry, you know. You look at things and look at something as simple as a valve guide. What happens when there's a sharp edge on it?
So this is a common failure that we see. This is looking at the titanium valve here with the moly coating on it. And the interesting thing about that when we first saw it was like, wow, it's got this perfect break in it, and then this rougher one at the top, and you go, well, why is that happening? Ironically, we see this happen there at the bottom of the valve guide the most when the spring is out of control and we get a lot of valve bounce. As you have clearance between the stem and the guide and that thing doesn't come back on the seat concentrically, there's a bending moment there. And the moly, of course, is hard and brittle. And so we see that chipping right there at the interface between where the tie stops and the moly starts quite often.
And it's right there, and you'll see it right there. You can see the wear above it versus below it. You can see what part of it was in the guide getting worn down, what part of it was sticking out and never got. And you can see exactly where, when it got up at max lift and started to do the hoka, you know, and that it bit it, you know. And I mean, and this is the thing is, you know, you guys might not all be able to buy a profilometer, but there's a lot of microscopes out there. There's some super good ones. This examining parts, I mean, you just don't know. if you'd worked with me for 20 years, you would not imagine how much time I spent looking through a microscope. Just to see what the heck is going on here. Because these surfaces want to tell you.
And the important part about this is when you say microscope, people kind of get nervous and go, oh, you're thinking like
electron.
Scanning electron. You know, you don't need 1,000 power magnification to see this. I think that picture was taken at about 20x. So I mean, you know, you could darn near do it with a magnifying glass and see this kind of stuff pretty easily.
You could. So it gets to the point, you know, there'll be good optics on eBay, and we'll even show you some other stuff that, you know, a little higher end. But you know, measuring equipment is your friend. I have never regretted buying something to measure something well.
Yeah.
Okay. This is your new. This is.
This is my baby. You know, this is
the part where me and Ben sit up and we start learning like the rest of you guys from Billy.
Yeah, I apologize. I'm going to enjoy this way too much, guys. Surface metallurgy. You know, when we talk about metallurgy, everybody's looking like we started with a deep down in it. Well, deep down in it doesn't fail. Like when they make valve springs, you wouldn't believe how much time they spend trying to make the thing from when they pour the metal into the vat to when it goes into your engine to drive those inclusions deepest they can into the wire. So you get it's not the global metallurgy, it's the metallurgy where the stress is the highest that matters. And there's amazing things you can do that are good, and there's amazing things you can do that are bad to the surface metallurgy. Applied loads greater than material strength is when something fails. And it's, you know, it's just amazing how easy it is to alter this. So we're going to talk about the good stuff and we'll talk about the bad stuff. The most common, the ways to add compressive stresses are nothing but overdraft protection. You know, we all have checking accounts, right? Well, when you think about, you can get a third or more of your balance added to it. You know, for that compressive stuff we talked about, 150 to 350 KSI, you can add 100 KSI of material strength. So it's like adding 30% to your balance of extra overdraft protection. The ways we normally do that, shot peening, you see rolling, you see nitriding, but we can also take away from it. You can take away through it grinding or burn. You can take away through rust, any oxidation. You can take away with the hydrogen embrittlement. So Chris Osborne, I want to thank him for this slide. Pat sent this over. And it's kind of like the best illustration I've seen about what shot peening is. So what we're basically doing is taking a small steel shot, we're accelerating it, and we're bombarding the surface. So you imagine that, by the way, if you take a valve spring and like you have somebody goes, oh, I want to save a few pennies on a valve spring, I don't want any shot peening in it, you'll knock down the life by, you know, a factor of 10, a factor of 5 by not shot peening it. So you imagine it increases the internal stresses, and that's that overdraft protection. Internal stress, positive, steels don't generally, you can't smush steels into failing. You actually pull them into failing. Now you think on a camshaft face, well, I'm just pushing on it. You're pushing here, but then you're pulling on this lattice here, and that's where the crack happens. So you can imagine that what we're doing is compacting the material, we're moving the atoms closer together by doing this process. And you can imagine this little steel ball comes in here and it smacks the surface, right? And bounces off, leaves that little indentation. Under that little indentation, you've just pushed the atoms a little closer together so they can tell you that that's a... When you've heard about X-ray machines can actually measure the hardness of something, they're not measuring the hardness, they're not pushing on it, they're measuring the distance between atoms.
Right.
The distance between atoms is the hardness. What makes something hard is compacting stuff together.
A great analogy for that is, we're here in Indianapolis. So the guys at Oak Ridge National Lab in Knoxville, Tennessee, have this particle accelerator. It's pretty cool. So
Amen. Amen.
Yeah, it is really cool, right? To get an idea of the space between atoms, let's go even smaller. What's the space between an electron and a proton and a neutron in an atom? So if we take, hold on, if we imagine, say, a hydrogen atom, smallest one on the scale, by the way, and it's the size of a softball. and we say, okay, proton, neutron, they're together, and they're right here, monument circle. Do you have a guess to how far away the first electron is? 6 miles. Try Knoxville, Tennessee. That's how much space is inside everything. Because everything is made up of atoms.
Except for subatomic particles,
Yeah.
Yeah. Sorry, I'm a nuclear physicist by education, so I apologize when I get really geeky about this stuff.
You can't tell from the accent.
Yeah, they thought I was there on some sort of EOC deal, oh, you're a redneck, okay, yeah. I passed my comps though. So, you go in here and you keep hitting it, and you hit it. And what it does, it creates this beneficial compressive zone. It does it throughout the whole wire. Now, a spring is nothing but a big torsion bar. It's just a torsion bar wrapped around itself. So as it's running, the stresses are on the outside. And it's really the highest on the ID of the spring because it's a smaller radius there. But, it's a wrapped torsion bar. But we put this compression in there. Sometimes we do some damage to the surface, so what they'll do is come back with a nanopeen. They'll polish it and then come back in nanopeening, and they can create this double compressive surface. So if you imagine this plot over here, and this was all done with the X-ray diffraction machine. If you want to be really good at peening, you wind up having to buy one of these X-ray diffractions to measure this hardness, this residual stress in there. But you can see that red line up on the top, that's a normal peening. Up to about 4 thousandths, it's given us some good, but past 4 thousandths, it sort of messed us up a little bit, damaged it. But you get really good at doing these peening, you get more like the blue line. And you can see it's lower at the top, and the reason it's lower at the top is because that damaged the peening cost. It's made it rougher up there. So if you look at a modern valve spring, you'll see they're kind of shiny or pretty neat looking. Well, what they've done is they've gone in there and done the blue line, and then they polished it. They come back and hit it again, or nitride and done something again to add this other compressive layer. So you get that green line down at the bottom. And again, look, you can see that this stress is highest at the top. This is 2,000th of an inch. When you get down here 1/2000th, we're talking about 150 KSI. That's 150 KSI on something that's around 300 KSI. We've given ourselves another 50% stronger surface than we would have had without the peening. So it's amazing what that will do. But, that's really important with springs. But even stuff like, you look at the guys at Blueprint, Norris Marshall, they build these 383s, and it's really a neat piece. But some of the stuff they do for industrial is very budget-oriented. So what they found out is some applications we can just run a cast crank, some applications have to billet crank. Well, they found out that, hey, there's some applications so we can take this cast crank and we can roll the fillet and we can run more power. So the one on the right's a normal crankshaft without the rolled fillet. The one on the left is the rolled fillet. Look how much better the surface is as you burnished in with that rolling that fillet in there. But not only have you burnished it and made the surface finish better, you've created these compressive stresses. And the guys did some stuff that was pretty cool with that. They actually took their in-cylinder pressure measurement, stuff that Ben does, and they went ahead and measured to figure out, okay, what's the pressure on this crank? And they modeled it up there on the left to figure out this blue. Well, what's the applied force on it? And they wrote, figuring out crank failures and running engines, I don't know if you guys know this, but it's kind of expensive and ugly and uses up fire bottles and all kinds of bad stuff. So what they did is they had some people come up with this deal that has like 2 tuning forks. It's 2 big steel plates on a crank, and they cut a section on it. They bolt these on it, and they drive it with about 1,000th of deflection at real high frequency. And it creates that same stress in that fillet that you would in a running engine. And they can correlate back and forth from cylinder pressure to how they drive this tuning fork to actually model exactly what's going on. And it's just a cool piece because they go in here with all the strain gauges, make sure it works. And there it is over on the left. And what they'll do is they'll have a bunch of cranks that are done and have the fillets rolled. And each time they can go in there and run it and check on what it does. Now they even have a metallurgy lab where they can section the cranks and they can go and check the hardness with a micro hardness gauge in that fillet and look and see what the compressive stresses are in the fillet too. So it's been a real cool thing to work with them on the rolled cranks. At Comp, we did a whole lot of stuff on plasma nitriding. Same thing, instead of hitting it with shot, now we're taking atoms, we're taking nitrogen atoms, and we're linking them together, and we're accelerating them into the surface. And some of them go deep in the surface like arrows. That deep in the surface like arrows is that transition zone, and it can be up to like 10 thousandths deep. Then you have the diffusion zone where it comes in there, and it might be 2 or 3 thousandths deep. Then you have the compound zone where they kind of lay on top. That's often called the white layer, and it's only a few tenths deep. So this is a rocker arm that's been nitrided that we've sectioned and mounted so we can look at what's going on with the different zones. And each zone is harder and softer, but it's added that compressive layer in there, and it's made it stronger. That's why you see nitrided crankshafts. You're like, okay, well, Billy, you can do good things you can do good things. How about bad things? Well, that's absolutely the same. When you're grinding a camshaft, it's really easy to put heat in it with a grinding wheel. And you can see, like, EPC helped me with this. This is like for industrial engines, and you can see when they do, to see what's happened to the structure, the easiest way to do it is to do nitric acid. And nitric acid will go in here and change the color of it. And so the process is called a nidal etch. And you can see after they run the nidal etch, you get that lobe that looks like this nice gray over there. If you have made it either harder through making it really hot and quenching it, or softer by burning it, by getting it hot and tempering it, it will change the color. And so you look at this next one, you can see put nidal etch on it, and it will go in there and turn black. Now, if you're just a dude racing and you think you might have a burnt camshaft, you don't have nitric acid, you can buy it by Pace, by the way, if you want nitric acid pre-mix and everything like that. Pace Technologies, I think, are Arizona. But you can go over to a glass bead cabinet, and if you shot it with glass bead, you would see that that part that looks black there would be soft, would look duller. And the reason it looked duller is because the glass bead would have gone deeper in the surface because it's softer, and show you that soft area in there. My friend Mark Eisler used to work, he works at Hendricks now, he was at Sterling Performance, and he used to get all his camshafts glass beaded. And he believed that the glass beading was letting the lifter grab better, and that's why they ran better. What's funny is I'm going, well, that's not it. So I start going out there and watching them, and when they were glass beading his camshafts, they'd see that where they were burnt, and they'd go back and re-grind them and grind the burn out. So he was getting camshafts that had all been ground like 2 or 3 times to make sure they slowed down to get the burn out of it. And like everybody else is getting burnt camshafts, and it's like, hey, look at this glass beading, I know this thing will go 5 times as long. No, it just wasn't burnt. And, you know, you can see with the nidal etch, like when Cummins or somebody like that, one of the big industrial diesels, they're all going to run through this process to look for grinder burn. Usually you don't see this blackened guy like the blackened chicken sandwich. You see this deal where you have a little bit going into the rank. CNC grinders go faster over the base circle. Sometimes you see dresser burn on the base circle. You can see where you dress the wheel. But this is how you can see, did I take anything out of it? Working with Roush Yates, sometimes that they get environments where coatings can have a lot of hydrogen in them. And you can see that when you do the hydrogen into it, the hydrogen, like nitrogen, can make the surface actually stronger. But it also makes it brittle like glass. And so these coupons, when they did one type of coating and tried to pull it apart, you can see how it didn't stretch at all. The part didn't pull out and tensile and then break. It just snapped. But you did a different coating, you could get it where it would pull apart. So they wound up having to do coupons with their coatings to make sure they didn't have hydrogen embrittlement. So there's a lot of things. Just like that, you can wind up with rust on your hand. You can do all kinds of things. Do the same thing that hurt the surface, make it weaker. You haven't changed the global chemistry. You've only damaged the surface, and it causes a huge deal. Do no harm. Okay?
Yep. Yeah, it's
handling of our parts is just as important as how much effort they put into making them, right? Mm-hmm.
Yeah, the examining it so much. If y'all are going to polish something or coat something, if you're going to do a cryo treatment, anything like that, talk to the manufacturer. Start understanding what you're doing, because you can really mess something up. Buying a microscope, buying a profilometer, looking at what's just going on. If you're going to go into super finishing, understand your super finishing. Not all super finishing is the same. There's super finishing that's done with electric. It's always something to do with the kinetic energy. You got to get energy in. Some people do electric. Well, electric's going to do some damage to the surface. Some people do the acid. The rim is the acid etching. There are some materials that you don't hurt at all by acid etching. But somehow high carbon materials, you'll leave carbides on the surface you acid etch. So kind of understand that. Some of them are kinetic energy. I love this shot that our buddy Nick sent. Do you want to go through a little bit of this? Because we've probably all done this, right? That, clearly this guy sent this rod back to Nick and said, Callies, and said,
why
this is crappy material.
Why did your rod fail?
Yeah. Why my rod fail?
So, you guys have all seen this. You grab the rod, you put it on, and you go, oh no, it hits something. It hits the cam lobe or it hits the side of the block. And so what you see here is where he started grinding on it. And you can see very clearly where that crack started because of where it was ground.
Mm-hmm. Mistakes were made.
Look where that crack is right there.
Yeah.
Yeah.
Perpendicular to the stress.
Yes, he did. He created a perfect, like when you perforate paper when you're in elementary school so you can rip it out, this guy had perforated rods and was totally clueless.
Yep.
But they told him, expensively, but you can see it follows that angle exactly.
So mistakes were made. We can only hope lessons were learned.
Yeah.
No doubt.
We can't guarantee that, right?
No, that part's, yeah. Go ahead,
Some
keep
of
going.
this. Dude, I've talked so much, but some of the stuff you do with your microscope, I love the vision system you have.
Yeah, this is a picture of, there's lights everywhere.
Yeah, they are.
Yeah, we said we're going to fall one of us, so.
Yeah, this is just a picture of the type of microscope. We keep talking about biomicroscope. What does that mean? Well, this is one that we use at EFI University at the school, made by Vision Engineering. Ours is called the EvoCam 2. These aren't extremely expensive, probably in the neighborhood about $11,000 or $12,000 you can buy this, and depending on which lens you change, you can get anywhere from, I think we can get up to about 160 power, like normal glass magnification, and then digitally magnified up to about 1,000, but to be honest, that's not very useful because after about 300 it gets so grainy and granular you can't see a lot. But that said, 90% of the stuff you're looking at, whether you're looking at piston rings or valves or bearings, or in this case, the valve head that failed here from high cycle fatigue, you're only at between 25 and 50 power. So, for a shop that's doing a lot of work, it's not exorbitantly expensive to have this kind of equipment. So,
But you talked about like a $12,000 investment in a microscope. Now, I don't know about you guys, my eyes are not as good as they used to be.
So this is probably my favorite piece that I have in my shop that I keep right there next to the scope that I found one day when I was running the Spintron. And that's a normal, just stamped LS, valve keeper there. And on the left, you can kind of see it with no magnification. And so I keep that to this day. And you come to my shop, I'll hand it to you, and I dare you to find that crack. But what had happened was, I was making runs on the Spintron, and you're doing your checks, and you take a spring off, and just kind of check everything. When I went to put it back together, it just didn't feel
right. When you pull the retainer up and everything.
Yeah, something just felt weird, and I looked at it, I don't know, I can't see anything. And then as I went to put it back together, I thought, it's free to take this over and just have a second look under the scope. And I about fell off my chair when I put that thing at 20 power and started to focus and zoom in. So, a $10,000 or $12,000 microscope saves a $40,000 or $50,000 catastrophic engine failure. That thing was 1 or 2 runs away from
all the magic smoke was coming out.
Yeah, absolutely, yeah. So we try to look at everything. Here's looking at some bearings, and like I said, we looked at valve springs. Here's a great valve spring failure that we had last year. I think it was last year or the year before on Robbie Blankenship's car. We had been running the same setup for quite some time, and then
these were good expensive springs too.
We're not, it's an almost inch 100 lift and 10,800 RPM. I mean, a pretty serious thing.
They wanted $150 a set.
No. No. And so this is one of those things where, like, all of a sudden in the middle of the season, we start randomly having spring failures. And so you got to scratch your head and go, why? What changed? What's different? And so I'd sent this actually went to Aaron White. He got some of these images for us. But if you look at that drag mark there where the spring came out of the tooling and the tooling just wasn't adjusted properly and it was just dragging the inside of that coil there, well, you can see it up in the top here. I'm going to walk over here.
Yeah.
You can see the indentation here where the tooling was dragging, and you can see where the crack started. If you follow it up there, it leads right to where the crack began. And so that was a defect that was in the spring when we got it that, frankly, we just didn't see. But after the fact, now we have something new to inspect. Every spring comes out of the box and goes right in the microscope, and you look for those kinds of things. And again, that's, the top one there you see is probably only about 20x or something like that. You don't need a scanning electron microscope to find some of these failures. And this is what I would call, looking for that kind of stuff is finding the failure before it fails.
Yeah, right? And you would have found that with the eye loop if you looked hard enough.
Yeah, sure.
Now, it's a whole lot easier. Eye loops make great shot. No, never mind. When you have a good microscope, you won't ever touch your eye loops ever again. But you see, old guys like me will have eye loops on their desk because, but
I still keep a little handheld magnifying glass next to the scope because oftentimes you just look at it and you go, oh, it's right there. I could have seen it.
No, but just looking at parts, you just can't imagine. This happens at the NASCAR level. I mean, the problem is with valve springs is you can't bend them with plastic tools. That wire just won't bend with something real nice and soft. So they have to use fairly sophisticated tooling, and it's pretty easy to put some damage into it. And if the guy's just not on his P's and Q's, you need to check your parts too. Because your reputation is on the line as an engine builder when something goes wrong.
Well, so that's the point I was going to make. So when we discovered the reason for this failure, right, it's really easy to go, doggone it, that spring guy, he made a crappy spring. Is that really his fault, or is it my fault as the engine builder because I didn't catch it before I put it in the engine, right? So that could have turned into a catastrophic engine failure. I mean, you're doing over 90 complete engine cycles per second, and when something like that fails, there's a whole bunch of other things that try to occupy the same time-space, what do you call it, time-space continuum?
Yeah, the two pieces try to occupy the same space at the same time.
It doesn't work very good. And so really now that became another, the product instead of the process, right? The old process was you get them out, you kind of look at them, you dust them off, and we just didn't put that much effort into it. But finding this and then going back, and we found it was an entire, I think we had 7 sets of springs that are all brand new sitting on the shelf that had that issue. And so it would have been way easier to find that before it went into the engine than this way. So.
It's kind of like FAA regulations. They're all written in blood.
They're written in somebody's blood.
When you start looking at things, if you start looking at your parts, it's so much better to catch it before, an intake valve goes through your intake manifold.
It's way cheaper that way, yeah. So you talked about DLC, right? So.
Well, yeah, unfortunately, in this one you can't look at a microscope and find.
Right.
Until after it's failed. I'll just put it out there. As the slide says, not all DLC is the same. There are single-layer DLCs. There are multi-layered DLCs. There are doped DLCs. That they all vary. And so just because a part is DLC'd doesn't mean that if you've had success using, say, a DLC-coated wrist pin, that I'm going to go use that same DLC on a cam lobe or something else, that it's going to do the same thing. It absolutely won't. It's a big variable here.
And the surface has to be, like you see this failed because there's too big a chamfer on the lifter, but the lifter itself was too rough to begin with. So if you you put a hard DLC, it's about 3,000 Vickers. The hardest steel is less than 1,000 Vickers. So paper, rock, scissors, it's going to win. So you put a DLC on a rough surface, it's a cutter. The other thing is the DLC is really hard, so you have to put it, most of the parts of DLC, you can't just DLC every material. You can't take a cast iron cam and put a cast iron lifter, put DLC on it and think it needs to work. It's not hard enough. It's going to try to flex. You wind up with these really high-end marging steels that have been nitrided to try to get up close to that 1,000 Vickers, and they put like a 1,500 Vickers layer with a tie nitride before they put DLC, and they put a DLC 3 before they do a 4 to try to get that hardness to be a spectrum instead of a DLC. But one thing, once you start cracking a DLC, because this goes back to our surfaces thing, when you crack a DLC, what do you think that does to the steel underneath it? You're putting a stress in it. You're giving it a place just like a razor blade to start a crack. So you get a crack in a DLC, it's going to transfer your metal. So you got to be really careful with your coatings. Coatings are wonderful, but they are not a cure-all.
No, they're not. They're a definite advantage, but they're not magic pixie dust.
Right, and they're very much part of this whole surface deal.
That great coating won't fix a bad surface.
One other thing too is an extra variable with the different types of DLC. They actually react with different additives in the oil. So if you have oil A and you're using DLC A, and this guy's having success, and the guy's over here, he's using oil C, he starts using DLC A, and all of his parts fail. Why? Well, the chemistry is different, and they don't all act the same. We've seen it. I've seen it personally, and I have a friend of mine that's in the industry that's seen the exact same scenario, 2 different brands of oil, but they had the same additive chemistry added to it, and with the same DLC, they were failing parts left and right.
Right, and that's why we took the phosphate out when we did the flat tappet test. The reason it didn't have the Parco on it is that phosphorus and zinc that you put on the surface changes the chemistry, and we want to try to isolate variables. You know, when you're ever doing a test, you try to get rid of all the things that you don't know, so you can look and try to learn something.
So guys, you know, if you've ever given a public presentation, you know that it's a lot of work and it's a lot of challenge to get up here and do it. It's 10 times harder when you do it with 3 people, and so it's. I hope it's come across that we put a lot of effort into the collaboration of putting slides together and what point we wanted to get across and wanted it to be applicable for you. So, you know, we've done a really good job. I'm impressed that we've used up only 1 hour and 20 minutes of our 1 hour time limit. So that said, we truly hope that you got something out of this that makes you think a little bit more about your surface finish, your preparation, your process versus your product, and, you know, how to continue growing and looking at things a little bit more than we looked at them before. So that said, do we want to take questions?
Yeah, and then just know that this was sort of, we were trying to do something like an all-you-can-eat buffet, where we threw out a little lobster over here, a little steak over here, and things. Most people don't ever try to do all 3 of these parts of surface. They'll do one, they'll do topography, they'll do contour, they'll do the metallurgy. They won't do all 3 at once. But one reason we wanted to do this way is to give you guys an idea. It's none of those 3. It's all of those 3.
3 sisters.
Yeah. So. And if you mess up one of them, it does not matter how good you did on the other 2.
No. People who've heard my oil talks in the past know that when we talked about ZDP, I had one rule. There's no amount of zinc can fix bad geometry.
Ever.
I think we all thought it there, right?
Unscrambling an egg.
Yeah, it's just not going to happen. But hopefully, too, the lessons from the day also give you a different lens to look at part failures. Hopefully you never look at a failed part the same way ever again. Now you have a whole list of things to go through in your mind and to begin to evaluate what you're seeing so that you can make a better decision.
And know it probably started, there's like better than a 90% chance your failure started in that first 10 thousandths. So, you know, start thinking about why was the load high here? One of the things I start to do, like when somebody sends something that's all blown up, I try to look at all the other parts. Like that connecting rod we saw that Nick saw the crack in, that wasn't the one that failed. That was the one that was about to fail. Mm-hmm. Yeah. And I'm sorry, could you have a question? You had one and everything, yeah.
What is DLC?
Diamond-like carbon is what it's the idea. It's a physical vapor deposition process. You put something in a vacuum, you heat up the carbon, and it attaches to the surface. And so what they do is like a tinitride, that gold coating you see on tools. The reason you don't see that on like engine parts is because it's kind of abrasive. That's why it works really good on tools. So they'll put that on there. They'll put either a silicon nitride or a titanium nitride on the part first to adhere to the part, and then they'll evaporate the carbon on it. And when I say C3 or C4, it's how many carbon atoms are locked together in the coating. And the C4 is the hardest one, the best lubricity. You know, there's a whole study called tribology. I know it. The book is How to Lube an Engineer. No, lubrication for engineers. Here's a certified tribologist right here. But that whole study about the lubricity of it, and DLC, diamond-like carbon. I'm sorry.
Yep.
Yes, sir.
I've got a question about probably the early slide.
Yes.
Excuse me, the one that Lake you can tell about.
Yeah, that good one. Yeah. Go back to the lake slide.
The 3D.
The pretty colorful one.
Yeah.
That thing's pretty awesome. There you go.
So I understood what you said about where the ring stops.
Mm-hmm.
You know, you can see the RPK still there. But what's going on with the valley? Why is the valley still there?
Okay, so that's a great thing. If this was actually, because it's looking at the surface and going that way, and it's actually taking the data and it's moving it to the top. So the orientation of everything it's seeing optically is moved to the top. If we move this and flipped the orientation to the bottom, where we began from the valley, you would see a different change, because it would actually round down. If you This is just one view of it. If you look at another view where it's down, it looks like a rainbow.
Yeah, this whole
from
surface
side to side.
is really down a little bit and then
Yeah.
comes up. So these
Right.
valleys are actually, would be the same
Yeah,
depth.
it's taking that data and trying to move it to a fixed location.
There's a bunch of math that happened.
Yeah.
And Mark's already left, so we can make fun of him. Tell him that his math isn't right. Actually, I'll pay you to record.
That's not his software, no.
Actually, I'd just pay you to tell him his math's not right, just to watch him. Yeah.
Just see him twitch.
Record it. Oh, it'd be, yeah, because he's the nicest guy ever, and he's not going to want to cuss you, but he's going to want to, and it'd be so much fun to watch.
That help?
So what you're saying is the valley's all still there?
Yes.
Yeah,
Yeah, it only wears down, it doesn't wear up.
yeah.
Yes, sir.
So I've seen a lot of DLC-coded flat tappet lifters coming available, and I'm just wondering if there's any different steps you need to take when you're doing break-in procedure on that, and or if there's any cans or materials in cans that you want to avoid when you're selecting a lifter like that. Like say you're running a flat.
So what kind of material?
No, honestly, it winds up where you can do almost anything. You know, like the Cup guys all did, they did their camshafts out of PM M4 tool steel, or they did some R-aging steel and nitride. They did really hard stuff, and they would even, for lower friction, they'd DLC the camshafts. And so you'll hear these rumors. They'll say, I'm sure you could go on some website or, oh, you kind of run a tool steel. No, you don't. The reason they had to do that is because they were running 600-pound open springs with 2.2 to 1 rocker arms, which math does work, and that does multiply the forces. So they were seeing 5,000-pound push rod loads. And 5,000-pound push rod loads would not work on cast iron. But if you're running the same cam profile and the same rocker arm and the same valve spring, you can run the same cam material on with DLC lifters that you could with the flat tappet. So we've done a lot of testing with comp when I was there doing flat tappet cams with the DLC. It works great. You do have to still do the thing. You can't mess up the surface. You still got to do everything right. There is a little break-in when you do it because it does have to go into match. It's not as much as you had before, but if you're on cast iron cam with DLC, there's some break-in. But you can also run 5160. You can run 8620.
Yeah.
You can you can almost run any steel camshaft that would work for a roller, or any steel camshaft that would work with that spring load with a flat tappet, with the DLC lifter. Does that make sense?
If you're going to do DLC lifters, you'd want to use the high zinc, like over 1,500 part per million zinc, just for that first 30 minutes, and then get it out. And do not run an oil that has that high a level of zinc continuously.
Right.
You want
and
to
we
be
talked about like
that
on
1,000 or so, lower number is where you want to be, because it doesn't need as much. So when you give it to more, the chemistry now starts attacking the other surface and causes more cam wear, so you don't want that.
Right. And Chris Potter's back here, and he's been working a lot on this. I know that the guys at Comp have really worked a lot. But it's like, do you want to Parco the camshaft, so that when you Parco it, you're doing an acid annealing of the surface that lets it work in quicker to mate those surfaces. When you do DLC, well, probably. I don't know. We've done it both ways. Usually when we're doing testing, we do it without Parco. Why without Parco, Billy? Well, yeah, because that's the worst case scenario. You're not putting something to make it break in quicker and everything like that.
No help.
Yes, no help. Yes, sir.
Yeah, I guess this is to Blake. I have an engine that gets a lot of condensation in it. And then it will stick on the springs, and then when we pull it down, I have rust on